hey there, everyone. How are you? Hope you're doing well. We're actually going to start doing optimization now. And in fact, I think I might actually do 3 videos in one right now. I know. What the hell are you doing that for, Kukla? Well, because I don't actually know when's a good place to stop. Um, and so I'm just going to dig in and we'll go through all the optimization questions. And, for you, it could be, tired of watching, I'll watch more later. And that could be a great stopping place. But since that will be a different point for all of you, then I don't know. But I can say that all of these are pretty classic and you should be comfortable with all of them. Um, Maybe one or two that you don't have to worry about, but yeah, optimization. Okay, so what we're going to be doing now is actually applying all this knowledge about derivatives, including that stuff about finding maxes and mins. Yeah, that's what optimization means. It means that we're going to be looking for the optimal amount. Maybe that's the least cost, maybe that's the greatest profit. Yeah, there we go. So let's take a look at our problems. So the first one says this. Find the smallest perimeter for a rectangle whose area is 16 square meters. What are the dimensions of this rectangle? Okay, so let's think about what we know. Smallest perimeter. Perimeter is 2 L's plus 2 W's. Area is L times W, and area here is 16. That's my helping equation. See this? See this superlative? This superlative tells me what I'm taking the derivative of. I'm looking for a minimum on the perimeter function. Here's the perimeter function. This is the one I want to take the derivative of, but not until this is in terms of one variable. So I'm going to use helping equation over here and solve helping equation for one of the variables, 16 over W equals L, so that I can plug that in here. P of W equals 2 times 16 over W plus 2W, or 32 over W plus 2W. There's my perimeter function. We've done the hardest part of this problem now. I think the calculus part of this problem is much easier. The pre-cal part, I mean, we did a problem like this last year. So the pre-cal part is where I have to say, okay, this is the thing I want to take the derivative of, right? This superlative here tells me take the derivative of that. This number associated with area tells me you're going to be a happy helping equation to help me rewrite the one that I need to take the derivative of in terms of one variable. Great. So I got this perimeter function, but I want P prime. Why? Because I'm trying to find the minimum on P. So I need to find the critical points on P prime. Ooh, there's one. W equals 0. If W equals 0, then I get undefined. And so I know derivative is undefined when W equals 0. 0. You could, of course, say, Mr. Kukla, it's kind of stupid rectangle that has a width of 0. Yeah, I agree. I'll call it naive. But we still need to take this derivative. So this 32 over W is really that. So bring down the -1. So we have negative 32 W to the minus 2. And then if I take the derivative here, I get plus 2. So when is this equal to 0? Well, minus 32 over W squared plus 2 equals 0. So 2 equals 32 over W squared. 2W squared equals 32. W squared equals 16. And we take the square root of both sides, and we think, hey, plus or minus 4. But then you say, no, you can't have a w of negative 4. You can't have a negative side length. Come on. So our value for w, our critical number for w then, is going to be 4. And don't forget we've got this endpoint over here at 0. So these are w values, and I'm making a p prime sign chart. So what happens if I plug a 1 in here? I get negative 32 plus 2. Well, that's definitely negative. And if I plug 10 in here, 10 squared is 100. Negative 32 over 100, well, that's definitely less than 1. Plus 2, positive. Hey, look, my p prime sign chart goes minus plus. Guess what I have there? I have a minimum at p equals 4. Okay? And yes, it's a minimum, and so you get to write a justification. Perimeter is at a minimum when when w equals 4. By the way, if w equals 4, what does L equal? Remember that formula that we had? Area equals length times width, and we said 16 equals length times width, and we divided by w. We said, okay, length is 16 over w. When w is 4, 16 over 4 means the length is 4. So when length equals width equals 4, perimeter is at a minimum when these things equal 4, because to the left of w equals 4, p prime is less than 0, and to the right of p of w equals 4, p prime is greater than 0. All right, did we answer the question? They said, what are the dimensions? The dimensions are 4 meters by 4 meters. Okay. And did we do everything else? Did they ask what the... No, we know what that area is. That was given to us. Did they ask us what the smallest perimeter is? Yeah, I think they do. Find the smallest perimeter. So what would our perimeter be? If each of our sides is 4 meters plus 4 meters plus 4 meters plus 4 meters, the smallest perimeter is 16 meters. Not to be confused with 16 square meters. This is an area. This is a linear distance. This is you walking around the outside of the garden. Okay, next. Oh, so by the way, that was optimization, right? Optimization is really just finding mins and maxes. So remember this problem. Find the maximum volume and determine the size of the squares that need to be cut out to form the box with maximum volume. And, yeah, you've seen this one a bunch. Remember this one from last year where we were cutting out these corners? I know I do. X by X, X by X. So we're cutting out all of these squares. We've got that this side is 16. We know that this side is 10. And if we fold along the dotted lines, remember that that's going to make us a little open-topped box. Okay? So this is that. How long is this? Well, this is 16. This is x. This is x. So this is 16 minus 2x. This is that. Well, this is 10. And this is x. And this is x. So this has to be 10 minus 2x. And finally, This is that. So it's just x. So my volume is x, 16 minus 2x, 10 minus 2x. There's my volume formula. Remember doing this problem many times in pre-cal? I do, but maybe you didn't. Um, so let's see what we can do with this. So if I think about volume in that pre-cali kind of way, I've got zeros at 0, 8, and 5. So 0, 8, and 5. 5, 8, 0, volume, x. Now, do you remember us talking about the domain and how we threw away all these things because we can't cut a negative side length, nor can we have a negative volume, nor can we have a negative volume? And then over here, like if x was equal to 10, think about this picture that we're looking at. If this is x, and this is x, and we're going to cut two of these, and the whole side is 10, if I cut 5 and 5, I'm left with no side length. So if I try and cut 10 off of this side and 10 off, no, I can't. 5 is the most I can do, which is why we're really only looking at this part of this volume curve. This is all garbage. I can't make these, nor can I have the negative volume. And here is my only successful domain. So I've got endpoints. My endpoints are 0 to 5. But in order to find where this maximum is, because we learned last year it's not halfway in between these, we're going to have to take the derivative of volume. So I need to find volume, but I ain't doing some three-way product rule thing. Instead, I'm going to distribute that so that volume now equals 16x minus 2x squared. And either at this point, I'm going to use the product rule, or I'm going to FOIL. And I think I'm going to FOIL. So v equals 160x minus 20x squared minus 32x squared plus 4x to the third. Combine some of the terms. V equals 4x to the third minus 52x squared plus 160x. Take the derivative. 12x squared minus 104x plus 160. I feel like I did that problem a little while ago. I can take a 4 out of each of these, and I'm left with 3x squared minus 26x plus 40. And that, 3x minus 20, x minus 2, and there's a 4 out. So I've got critical points here and here. Now, 20 thirds is bigger than 6. That's over here. This is 20 thirds. So, f prime is equal, v prime is equal to 0 there, but this is outside of the domain of my problem. This produces a negative volume. And no, sorry, I can't do that. So x equals 20 over 3, x equals 2. That's garbage. That's my candidate. I'm just going to have a v prime sign chart with 0 on one end, 5 on the other, and 2. So when I plug in, say, 1 here, 1 minus 2 is negative. 3 minus 20 is negative. Negative times negative times positive is positive. But if I put something like a 3 in here, this is still negative. But now this is positive times negative, and I get negative. And so, yes, I really do need you to write the justification sentence. Volume is maximized when x equals 2, because to the left of x equals 2, v prime is greater than 0, and to the right of x equals 2, v prime is less than 0. I'm still writing that justification sentence. Now, did we answer the question? Determine the size of the squares. We did that. Ooh, it says find the maximum volume. We haven't done that. The volume is maximized. I might want to say the maximum volume is, and then put that number instead of writing a second sentence. So 2. 2 times 2 is 4. 16 minus 4 is 12. By 2 by 2 times 2 is 4. 10 minus 4 is 6. So those are the dimensions. Length times width times height, or length times height times width. So I got 72 times 2, or 144. And did we have any units here on this? No, we did not. So 144 square units is the max volume. Okay? Make sure you answer the questions being asked. Now, let's think about this for a second. I mean, like the whole sort of, what are we looking at? There's a whole bunch of pre-calc where I had to write a volume equation. The calculus was only, once I had that volume equation, taking the derivative of that volume equation and finding a max. Yeah, no problem. The calculus part of this is the easy part. The pre-calc part is the hard part, which is why we did that box problem 3, 4 different times. I know it showed up in at least 2 homeworks. I believe we did it in one of the classes. It was on the review stations, and it showed up on the test. So yeah, you've definitely seen that before. And guess what? You need to become acquainted with it again. All right, next problem. Remember this one? What are the dimensions of the box with maximum volume whose girth plus length is 108. And we want inches here, don't we? Yeah, these are inches. So let's think what we're talking about. Oh, by the way, it's a square-based box. And we want to find the maximum volume of this. And we have this restriction. Girth plus length is 108. Now, I know that each of these is x and this is y because it's in the picture. And so I can say girth is the perimeter of the cross-section. And guess what? You learned that last year when we did this problem the first time. You learned it again when we did it the second time in the polynomials unit. And now you've forgotten it again. So please, girth is the perimeter of the cross-section. For x, the length is y equals 108. Is this the thing I want to maximize? No, I want to maximize volume. What's the formula for volume here? Volume is length times width times height. And so volume is going to be x squared y. But I really want volume all in terms of one variable before I take the derivative. Oh, if only I had a helping equation to help me rewrite this volume in terms of one variable. Why is it that I want this in terms of one variable and not this in terms of one variable? Well, I'll give you 2 reasons for that. One, I don't know what y is equal to here. I could divide both sides by x squared, but dude, I don't know what volume is. But over here, I have a number. Second, I want to maximize volume. That means I want to take the derivative of volume. I need to take the derivative of this thing, not the derivative of that. So I'm going to say that y equals 108 minus 4x. And so my volume equation then is going to be x squared times 108 minus 4x. And conveniently, this is now in factored form. So let's think about this graphically. If I were to distribute, I would have a negative 4x to the third. I see a bounce at 0 and passing through over here at 27. This is volume. This is x. That's my maximum volume. Why not over here? Well, I can't have a negative side length. And no, I can't have anything here with a negative volume. So I'm looking for this place. How do I find that max? Just take the derivative of this. Again, you can use product rule here, or you can distribute minus 4x to the third plus 1 over 8x squared. And when I take the derivative, v prime is going to be negative 12x squared plus 216x. Does 12 go into 216? I think it does. 216 divided by 12. That was not that. 216 divided by 12 is 18. Okay, so I'm going to take out a minus 12x and have x minus 18 here. So I have zeros at 0 and at 18 on v prime. So 0, 18, v prime. Look, a volume of 0. Yeah, I'm not looking over here. I'm just, I'm sorry, that's when x equals 0. Yeah, if x equals 0, I don't have a box anymore. And I certainly can't have negative x's. So hard end there. Now, what happens if I plug in a 10? 108 minus 40, that's positive. 10 squared, that's positive. Positive times positive, I get positive. If I plug in a 20, 20 times 4 is 80. That's still positive, and that's still... Are you sure, Mr. Kukla? I feel like I got something wrong here. Oh, why am I plugging those into... Sorry. You should not test v prime in v. Okay, so we said that v was minus 4x to the third plus 108x squared. I think there's 108x squared because this goes in there. I distribute that. Yes. And so we said v prime was negative 12x squared plus 216x. We factored out a minus 12x, and we have x minus 18. But this is v prime. That's what I want to plug a 10 into. So if I plug a 10 in there, 10 to minus 18, though that's negative. That's negative. I get positive. Good. But if I plug in a 20, 20 minus 18 is positive 2 times this negative number. So negative times positive is negative. So I can see my volume is maximized when x equals 18. And so then I do, the easy calculus part. I say volume is maximized when x equals 18 because to the left of x equals 18, v prime is greater than 0, and to the right of x equals 18, v prime is less than 0. Okay, and what were we asked to do? We wanted to know the dimensions that give us the maximum volume. We didn't need to find the maximum volume this time, we just need the dimensions. So remember that this was x, this was x, this was y. So I can say 18 by 18 by, what's y? Convenient helping equation strikes again. So y equals this stuff. If I plug my 18 in here, 4 times 18 is 72. 108 minus 72 is 36. I think so. 108 minus 72, yeah, 36. So by 36 inches. Ta-da! There are the dimensions of the box that maximize the volume given this constraint, or helping equation. Helped me twice. All right. Sure glad we did that a lot last year. Well, look, another problem we did last year. You have 200 feet of fencing. You'd like to build a corral. This is y, this is y, this is y, x, 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 x. We've got 200 feet of fencing to make all those sides. And what we want to do is maximize area. We want our horse friends to have plenty of space. The most space we can get them, even though we only have this amount of fencing. So let's think about this fencing equation. We've got 200 equals 3 of those y's plus 4 of those x's. But what we're trying to maximize is area. Yeah, not perimeter-y thing, but area. So what's the area formula for this rectangle? Length times width. Well, the length is x plus x, or 2x, and the width is y. So this is the one I want to take the derivative of. This is the one I want to get in terms of one variable. So this is my helping equation. So I've got 200 minus 4x equals 3y, or that's what y equals. So y is 200 minus 4x over 3. Fabulous. Now, do you want to distribute? Do you want to use product rule? I don't know. I think actually I want to split this back into two fractions. 200 over 3 minus 4x over 3. And then I want to distribute. So I'm going to have 400x over 3 minus 8x squared over 3. And there's my a. In fact, I kind of want to take out that 1/3. Maybe a 4 or an 8. It goes into that. Oh, let's take out 8/3 and an x. No, don't take out the x. Just take out the 8/3. In fact, just take the derivative. The derivative of this is going to be 400 over 3. And the derivative here, I'll bring down that 2, is minus 16 over 3x. So there's my derivative. I want to know when this derivative is equal to 0. And so let's set this derivative equal to 0. I'm going to have 400 over 3 equals 16 over 3x. If I multiply both sides by 3 over 16, I get x equals 400 divided by 16. Isn't that 25? I think that's 25. 400 divided by 16 is 25. So I've got this 25 as a value of x on my a prime sign chart. I got a hard stop here at 0 because I can't have, talk about being cruel to the poor horses when you make that side length equal to 0 for them. If I plug in a 1 into a prime, 400 thirds minus 16 thirds, that's definitely positive. But if I put in a number over here, something that's bigger than 25, I don't know, 30. 30 divided by 3 is 10. 10 times negative 16 is negative 160. Oh, no, 30. I was doing 30. 10, 160. Oh, but I cancel. Yeah. So if I plug in a 30 here, I have negative 480 plus 400. Well, 400 minus 480, I'm sorry, that's negative. So again, I have a maximum of covering at 25. So let's go. Area is maximized when x equals 25, because to the left of x equals 25, a prime is greater than 0, and to the right of x equals 25, a prime is less than 0. Okay. What were they asking for here? They said, what's the maximum area? Okay, well, I don't know what the maximum area is yet. All I know is the x value that produces it. Do you remember our area formula was 2x times y? I got the x value. How do I find the y value? Well, that's what this equation is for. Remember, y equals? So if I plug a 25 in here, 4 times 25 is 100. 200 thirds minus 100 thirds is going to be 100 thirds. So I can say that this is 100 over 3, and this is 25. And so my maximum area is 25 times 2 times 100 over 3, 50 times 100, 5,000 over 3, and I believe these are all feet, so my maximum area will be feet squared. This is the max area. Okay? And that's actually bigger than a lot of people's homes. So, yay, happy horses. Okay, anything else for that one? Nope, that's 4. All right, next. We've got, oh, this is a great question. Like, I'm sure you've wondered this and will never admit this to another human soul. How close does the curve y equals square root of x come to the point 3/2 0? I know, right? Okay, so here's my square root of x graph. Here's the point 3/2 0. Look at the distance from this point to that curve. How close? What's the closest? What are we trying to closest minimize? We're trying to minimize the length of this segment. Look at all those. Those are all distances from the point to the curve. And we want the closest. So what is it that we're going to take the derivative of? What is closeness? That is distance. Distance formula is what I want to take the derivative of. The distance formula, remember, d squared equals x minus 3/2 squared plus y minus 0 squared. Or d equals square root of x minus 3/2 squared plus y squared. Now, I don't actually like doing this, and in fact, our book encourages you not to do this. But instead, because the answers will be the same, that you use this, okay? You want to minimize this. Don't do that. I mean, you can, but really, just, go for a walk in the nature or thank mom for making you. Those would be better things to do than dealing with that chain rule nastiness. Okay, so what do we know? Well, right now my distance is in terms of 2 variables. Where's my helping equation? I need to get this all in terms of x. Oh, there it is. That's my helping equation. So we had d squared equals x minus 3/2 squared plus y squared. And we're replacing y with square root of x. So we have square root of x squared. Okay. So now what am I going to do? Well, I actually am going to FOIL that and say that d squared equals x squared minus 3x plus 9/4 plus x. So I'm going to combine these like terms. And no, I'm not going to factor. Instead, I'm going to take the derivative. Yeah, take the derivative. So when I take the derivative here, and that's very interesting. Because now I've actually put that there and taken that away. Okay, that seems tidier. Maybe I'm willing to do that. It's just an easy chain rule. So then d prime is going to be 1/2 x squared minus 2x plus 9/4 to the minus 1/2 times the derivative of the inside, 2x minus 2. Well, guess what? This is never equal to 0. This is never equal to 0. So my derivative is never undefined because that was on the bottom. This is never equal to 0. A constant is never equal to 0. This can be equal to 0. So d prime equals 0 when x is 1. This is the shortest distance. But I haven't shown that yet. I still need to provide evidence. So I've got a d prime sign chart. Of course, the distance is 0. And I'm sorry, the x value is 0. And then we came up with 1. Oh, what was my d prime? Did I do a d prime? Did I do a d prime? Yes, I did do a d prime. We had 2x minus 2 times that 1/2 times that x squared minus 2x plus 9/4 raised to that negative 1/2. Okay, so there's my d prime. And I'm going to plug in something over here, and I'm going to plug in something over here. So if I plug in a 10, this is still positive. Yeah, no, really, it's going to be. Because look, it's a square root in a denominator. I mean, this has got to generate a positive number, or I'm undefined. All right, you want to see it. 10 squared is 100, minus 20, that's 80. 80 plus 2 1/4. Yeah, 82 1/4, no problem. So that's going to be positive. I'm plugging in a 10. 20 minus 2 is 18. 18 times a half is 9. I got a positive on top. I got a positive on the bottom. I got a positive. Okay? Now, what if I plug in something like 1/2? 1/2 times 2 is 1. 1 minus 2 is negative 1. So negative times a positive times a positive, and that's going to be a negative. And oh, look, d prime goes from negative to positive at x equals 1, which means distance is minimized when x equals 1, because to the left of x equals 1, d prime is less than 0, and to the right of x equals 1, d prime is greater than 0. Can I just say, students every year say, Mr. Kukla, couldn't I leave that out? I'm tired of writing it. And so you know what the AP reader said to me in our Zoom virtual grading session together? They said to me, can I give them the point for this? Because they're saying to the right, and I don't know what they're saying to the right of. And I said, yeah, I agree. I can't give them that point. I need to know to the right of that point. Yeah, just write the whole sentence. You'd be so happy that you did, because it's bulletproof. Okay, what were we looking for? We were looking for the minimized distance. I found when the distance was a minimum, but I don't yet know what that minimum distance is. Though I do have now 2 ordered pairs, so I could use the distance formula. Let's use the distance formula and find the minimum distance. Distance equals square root 2 minus 1 squared plus, oh, not 2, but 3/2. 3/2 minus 1 squared, 0 minus 1 squared. So 3/2 minus 2/2 is 1/2, plus negative 1 squared is 1. That gives me 5/4. D equals square root of 5, or root 5 over 2. That's my minimum distance. That's the closest that this curve comes to this point. And this kind of thing is used to figure out those satellites, or we want to send that probe out into space. We want to get this distance as close as appropriate. And we can use our calculus to do that. And yes, therefore, calculus really is rocket science. You really are rocket scientists now. Okay, that was number 5. Number 6. Number 6 says the sum of 2 positive numbers is 20. Find the numbers if one number plus the square root of the other number is as large as possible. And then we'll do as small as possible. Well, that's a lot of words. Let's see if we can come up with some math. There are 2 numbers that add up to 20. So 20 equals x plus y. We're told that these have to be positive numbers. So x has to be greater than 0, positive. 0 is a positive. And y has to be greater than 0. So these are little sort of constraints on us. We can only add positive numbers to get that. Can't have be negative 1, positive 21. We also have this other tidbit here that one number plus the square root of the other number is as large as possible. Huh. As large as possible. Largest. I want the sum to be largest. This is the one I want to take the derivative of. This is my helping equation. So if I say that x equals 20 minus y, then I can have sum in terms of just y's. Sum equals 20 minus y plus square root of y. Okay, but now I'm trying to find as large as possible. We also want as small as possible. But one at a time, okay? So this is the thing I want to take the derivative of. Okay, so s prime, derivative of 20 is 0. Derivative of negative y is negative 1. And the derivative of this is 1/2 y to the minus 1/2. I want to know when this is equal to 0 or when this is undefined. It may be helpful to rewrite this as negative 1 plus 1 over 2 square root of y. Okay? So when I set this equal to 0, I've got 1 equals 1 over 2 root y. If I multiply both sides by that denominator, I get 2 root y equals 1. Divide by 2, root y equals 1/2, and then we square both sides. And a number of people do this in their head, and every time they do it in their head, they get y equals 1. But really, 1/2 times 1/2 is, in fact, 1/4, not 1. So it may be worth actually showing that step and thinking about it, rather than trying to do it in your head. So I get this one critical number. I mean, you can call 0 critical number. No, I can't put any negatives. I could do 0. Yeah, no. I'm going to go with just 1/4 on my S prime sign chart. Okay, S prime sign chart. We've got 1/4. And can't be negative. So if I plug in something, and these are y values, remember. These are y values, not x values. So we have 20 minus y here. And what did we have for s prime? We'll have to plug these values in. We have negative 1 plus 1 over square root of y. No, 2 root y. So if I plug in something over here like 1, square root of 1 is 1. 1/2 over, again, that's just going to be 1/2 minus 1 plus 1/2. I get a positive at 1. Okay, what about over here at like, I want something easy to take the square root of. Square root of 1/9 is 1/3, so I have 2/3 on the bottom. 1 over 2/3 is going to be plus 3/2. 3/2 minus 1, that's definitely positive. Did I get a positive over here? Oh, let's check again. I plugged in a 1. Oh no, I got a minus there. Yeah, I got a minus there because I plugged in a 1 here. Square root of 1 is 1. 1 times 2 is 2. 1 over 2 is 1/2. Minus 1 plus 1/2. That is negative. Okay, and so I see, oh, maximum. Nice. So maximum occurs when y equals 1/4. Well, I'm supposed to find the two numbers. Find the numbers. So I got my y value. How do I find my x value? Well, remember, x was equal to 20 minus y. So x equals 19 3/4. Okay? So we've got two numbers. I have them together. Well, no, it's the sum of the first one plus the square root of the second. And we were saying that this was the second number. Okay? So we have our maximum because S prime goes from positive to negative. I do need to write that justification sentence. The sum is as large as possible when y equals 1/4. You might want to say, and when x equals 13/4. You don't have to say that. You can just attribute to one variable telling you a value. Because to the left of y equals 1/4, s prime is greater than 0, and to the right of y equals 1/4, s prime is less than 0. Do we need to do anything else? We found the two numbers. Find the two numbers to make the sum as large as possible. We did that. But wait, then it says in the question, which I clearly erased when I have to write my justification, as small as possible. Well, how do I find as small as possible? Well, it turns out as small as possible is just asking for the absolute min. Well, this endpoint from here, because s prime is positive, s must be increasing. So that's a minimum. And over here, do I have another boundary? Yep, 20. So the function s is decreasing because s prime is negative. S is decreasing until I get to this point. So there's also a minimum here. Well, how can I figure out which of those is the smallest sum? Well, I have to go back to that sum formula. Remember our sum formula that was x plus square root of y? And then we rewrote it so that we had 20 minus y plus the square root of y. Okay, so let's plug in a 0 for y. If I plug in a 0 for y, I get 20. So s of 0 equals 20. And what about s of 20? If I take this 20 and put it in here, I'm going to, if I put in a 20 here and here, I've got 20 minus 20, which is 0, and then I have the square root of 20, which is 2 root 5. So which of these is bigger? Well, this is a little bigger than 2 times 2, a little bigger than 4. I'm sorry, that's a larger number. But since we're looking for the sum is as small as possible, yep, that happens when y equals 20 and x equals 0. Wait a minute. I wasn't allowed to have x equal to 0, I thought, because the numbers had to be positive. So, yeah, well, that's okay because that one was bigger than that one. So yes, there's my smallest sum possible is 2 root 5, and that happens when y is 20 and x equals 0. Oh, I can't have x equals 0. Oh, I'm a little concerned about that. What did we say? The minimum occurs when x is 0 or 20. There are two mins, one is 0, one is 20, but the absolute min occurs just like we said when y equals 20, x equals 0. All right, well, I'm going with that then. Next, problem number 7. Is your brain fried yet? You know, you may want to watch this whole thing through the first time and then just go back and have little tasty bits. I will tell you that we have how many? 11 plus 4 is 15 questions. So yeah, we've got a few more to go. Okay, we're about halfway there. New Pokemon for Christmas. So here's the thing. You are an elf, and there's a new Pokemon coming out, and you need to develop the new packaging for this new Pokemon. We want to sell it in a Pokeball. we want not to have to make another Pokeball. Our current Pokeball has a radius of 3. Curiously, the new Pokemon is called Conio. Hi, Conio. And Conio is a cone. And we want to know the largest Conio that we can fit into our Pokeball. Okay? So, many students make the mistake of taking Conio and drawing Conio inside the sphere this way. But you know, that's not necessarily the maximum. In fact, it isn't. So I draw Conio in here like this. Yep, that's my Conio. So the radius of the cone's base is not the same necessarily as the radius of the sphere. I don't know. Maybe they are. Maybe they are. So what am I trying to do? I'm trying to maximize volume. The biggest Conio that can fit inside of there. Okay, so I need a volume formula. Luckily, you remember the formula for volume of a cone is 1/3 pi r squared h, where this is h and this is r. And so 1/3 pi r squared h is my volume formula. But I would really like volume to be in terms of one variable. And curiously, it's not going to be one of these. So let's think about this. We know that the radius is 3. Well, I don't want to draw the radius that way. I want to draw the radius. And by the way, this is the center of the circle. Okay? The radius goes from the center out to the edge of the sphere. So this is 3. Okay? And yeah, that's my radius. And then this and this. So again, this radius, the radius of the cone, is not the same as the radius of the sphere. The radius of the sphere is fixed at 3. Okay? I do know that the height of Conio, this h, is made up of this little part from here to here. And what about from the center to here? That's 3 again. That's another radius. So I'm really looking at this right now. I'm looking at the radius of Conio. I'm looking at 3. I'm looking at x, and I'm looking at negative 3. Okay? So, well, that's fabulous. What information do I need for my volume equation? Well, it looks like my height is 3 plus x. But I also need to be able to describe this with the same variable. So let's use the Pythagorean theorem here. X squared plus big R squared equals 3 squared. Okay? And what am I solving for? R. So R squared equals 9 minus x squared. And when I take the square root of both sides, I see that R is square root of 9 minus. Isn't that interesting? Yeah, I'm pausing for a second because I have some different stuff here. Huh. Okay, well, let me see what happens. I've got R, and that was x squared. Okay. So R is square root of 9 minus x squared. We need R squared. R squared is just 9 minus x squared. Okay. So let's replace these things with these things. So volume is 1/3 pi. Radius squared is this one, 9 minus x squared. And height is 3 plus x. Okay, there's my volume formula, all in terms of one variable, x. Now, I need to find v prime. I need to take the derivative of that. V prime. I'm going to leave this out as a constant, pi over 3, and then I'm going to do product rule. So I'm going to have this times the derivative of that, plus this times the derivative of that. Okay, so I'm going to have 9 minus x squared minus 6x, no, minus 2x squared minus 6x. And I can tidy this up to be minus 3x squared minus 6x plus 9. If I pull a negative 3 out of here, so negative 3 times pi over 3, and what am I left with? X squared minus 2x, plus 2x minus 3. And so that's going to factor as x plus 3, x minus 1. Well, I can't have x equal to a negative number. So that doesn't produce anything for me. So x equals 1. When x equals 1, I think I have a max. But let's see. 1, v prime. So here's v prime. This is v prime. Let's plug in a 0. So when I plug in a 0, I get a negative times a positive, which is, I pull out a minus 3. I still have minus 5. No, that's a negative. Okay, I plug in 0, I have negative times negative, which is positive. And I plug in 2, and I'm going to have 4 plus 4 is 8 minus 3, that's positive, times a negative. Hey, look, I've got a max when x equals 1. Okay, there's a maximum volume when x equals 1. However, I'm asked to find the biggest conio. I want to know what's the biggest volume. Right now, I found out when the biggest volume occurs. It occurs when this distance is 1. Okay, so if x equals 1, 9 minus 1 is r squared. So r squared is 8, which means that r is square root of 8, or 2 root 2. Now what about h? Well, h is this distance. It's x plus 3. So we know that h must be, what did we say that was? This was 1. 1 plus 3 is 4. So maximum volume, v equals 1/3 pi 8, because it's r squared, times 4. So 32 pi over 3 inches cubed is the max volume. And don't forget, I need to write a justification sentence for that. What's my justification sentence? Volume, the maximum volume is 32 pi over 3 when x equals 1, because to the left of x equals 1, v prime is greater than 0, and to the right of x equals 1, v prime is less than 0. Now, for me, this is a really, really tough question. This is a very hard question. I mean, even just getting past the point where the cone might not be sitting on that great circle, because it doesn't. In fact, the cone has to go below in order for us to have maximum volume. You're not going to see this on a test, okay? But when you take the AP exam, if you haven't practiced and reviewed enough, some of their optimization problems feel like this one. This was so hard. How would you even think to do that? And the answer is, I don't expect you to do that. If this were honors calc, sure, I'd expect you to do that every day. But this is calc for humans. And in calc for humans, it's good for us to engage with this problem It's good for us to strive to this problem, but don't feel bad if this problem is like, he hadn't shown me, I wouldn't be able to do it. Okay? Really. I'm sure that was my response as well the first time I saw it. Okay, number 8. Find the dimensions of the largest rectangle bounded by the curve y equals 8 minus x squared and the x-axis. So let's think about what's going on here. We've got this downturn parabola. We've got the x-axis. We want to know the biggest rectangle we can put in. And there's lots of different rectangles. There's this rectangle. There's this rectangle. There's this rectangle. We've got lots of different rectangles that we can put in here. Well, we want to know about the largest one. And by largest, we mean area. So we want to maximize area of our rectangle. Now, like I said in pre-cal when we did this problem, there's a point over here called xy. This is y, this is x. There's another x over there because of symmetry. So my area formula here, area equals 2xy. All right, length times width, length times width. And area is the thing I want to maximize. I want the largest rectangle. But I don't want to take the derivative of that until it's in terms of one variable. If only I had a way to get rid of y. If only I knew what y was equal to in terms of x. Oh, there it is. A equals 2x, 8 minus x squared. Okay, or a equals negative 2x to the third plus 16x. There's my a, so my a prime, negative 6x squared plus 16. And so when does a prime equal 0? Well, a prime equals 0 when this equals 0, which means when 6x squared equals 16. That's 8 thirds. So x equals square root of 8 thirds, or plus and minus root 8 over 3. So this distance is root 8 thirds. Okay. That's an a prime equal to 0 value. So that's my critical number. Okay. So let's make an a prime sign chart and put square root of 8 thirds on it. Well, that's almost 9 thirds, which is almost 3. Square root of 3-ish is 1.7-ish. So this is smaller than 1.7. So I feel pretty safe putting in, I don't know, a 0, a 1 would be good. This is definitely, to get 1 here, we'd have root 3 over 3. So this is bigger than 1, and something bigger than this. The square root of 4 is 2, and this is smaller than the square root of 3. So I'm going to say 1 and 2 are my test values for a prime. If I plug in a 1, I get negative 6 plus 16, which is positive 10. If I plug in a 2, I get negative 24 plus 16 is negative. Aha! There I have a max. I can say area is maximized when x equals square root of 8 thirds, because to the left of x equals square root of 8 thirds, a prime is greater than 0, and to the right of x equals square root of 8 thirds, a prime is less than 0. Okay? We are asked to find the dimensions. So this is my x value. Well, what about my y value? Well, remember that y was equal to 8 minus x squared. So if I take this and plug it in for x, I'm going to have 8 minus square root of 8 thirds squared. Well, that's just going to be 8 minus 8 thirds. 24 thirds minus 8 thirds is 16 thirds. So x, the dimensions that maximize area are x equals square root of 8 thirds and y equals 16 thirds. Okay, nice. And what about if they ask us what is the maximum area? Well, what is the maximum area is me plugging in this x value here, or why don't I just multiply these two numbers together? Don't forget it was 2x, right? And so, oh, maybe we really want to think about that, right? Because the dimensions, because of that reflection, we didn't just have 1x, we had the 2x's. So I need 2x. There we go. And so my dimensions will be 2 square root of 8 thirds by 16 thirds. Those are the dimensions that produce the largest area. All right, biggest rectangle inside. Oh, and then I could actually multiply these and have 32 over 3 square root of 8 thirds. This is the max area. Okay. All right, that was number 8. Number 9, find the least amount of material needed for the cylindrical can whose volume is 1,600 square cubic milliliters. Okay, so least amount of material needed to make a can, cylindrical can with a volume of 1,600 milliliters cubed. Okay, so what's the formula for the volume of that cylindrical can? V equals pi r squared h. And yes, College Board does expect you to know that. So really, if you didn't know conio and you don't know cylindrical can, you should write them in your notebook on that page that I told you in August to write down, called Formulas I'm Supposed to Remember. All right, so this is not the thing we want to maximize. It gives us the volume. It says that the volume is 1,600. That's my helping equation. H is 1,600 over pi r squared. What is it that I'm trying to maximize or minimize? Least. Minimize. I'm trying to minimize the least amount of material. When I think about this can, and think about trying to make this can, it has a circle, and it has this lateral area. If I snip here and roll this out, I actually end up with a rectangle whose height is the height of the cylinder and whose circumference goes here. Okay, so this is the thing that I want to minimize. I want the least amount of, not just this, but this circle and this circle. So we call that surface area, SA. Many people just like to put this. So surface area is going to be the two circles, 2 pi r squared, plus this lateral area here, the area of this rectangle, which is 2 pi r h. And you know, I do want to show you this thing. Check it out. Surface area is actually 2 pi r plus h. Isn't that interesting? Surface area is the circumference of one of the circles times the sum of the height and the radius. That's kind of freaky cool, isn't it? I can get the surface area by multiplying circumference times the height plus the radius. Yeah, cracks me up every time. But what we want is the least amount of material. We want SA prime. But I don't want to find SA prime with two different variables. Pi is not a variable. Two different variables. We've got R's and H's. So I want to get rid of this H with my helping equation. I knew it was the helping equation because they gave me the volume. Whenever they give me that number, that's not the one I take the derivative of. The other one is. So let's replace this with 1600 over pi r squared. Oh yeah, there is some canceling. And here this with one of those. And so SA is going to be 2 pi r squared plus 2 times 1600, 3200 over r. So here's our surface area formula. Well, that's fabulous. Now, remember, we still need to take the derivative. All the work we've done so far has been algebra. And that's why we do all that algebra before we get to calculus. Now I want SA prime. The calculus should be pretty easy. Remember, this is 2 pi r squared plus 3200 r to the minus 1. So my derivative here, 4 pi r. And my derivative here, minus 3200 r. Don't forget to subtract 1. Don't forget to subtract 1. So that's my SA prime. Nice. Okay. I want to know when SA prime equals 0. So let's think about this. 4 pi r minus 3200 over r squared. This is SA prime, and I want to solve this for r. So, and when this is 0. So I've got 3200 over r squared equals 4 pi r. I'm trying to solve for r, so let's multiply both sides by r squared. We get 3200 equals 4 pi r cubed. And if we divide both sides by 4 pi, we get r cubed equals 800 over pi. Well, happy calculator time. Cube, no, I want to do parentheses. 800 divided by pi raised to the power of, I was taking the cube root, 1 divided by 3. Okay, I get that r equals 6.338. Fabulous. And here, look at my notes. My critical point was cube root of 800 over pi because I was too lazy to pull out the calculator. So I want to go back to SA prime. Maybe I want this SA prime. And I want to plug in some test points. SA prime, 0, 6.338, or cube root 800 over pi. So a number to the left of this, how about 1? So 3200 over 1 is 3200. 4 pi minus 3200, distinctly negative. If I plug in 10, here I'm going to have 40 pi minus, I plug in a 10, 10 squared is 100. 3200 divided by 100 is 32. Is 40 pi bigger than 32? Sure is. And so that's a plus. So I can see that surface area is minimized when radius is 6.338. Now, what did we need to find? Find the least amount of material. Oh, so they actually want me to find what the surface area is. Well, remember, surface area was 2 pi r squared plus 2 pi r h. And what was h again? Wasn't h equal to 1600 over pi r squared? Okay, so I've got this r. I'm going to plug that r in here so I can find h. And then because I want to know what the minimum surface area is, I'm going to plug that r and that h in here. I guess we could do that substitution. 1600 over pi r squared. And so didn't that become 3200 over r and 2 pi r squared? So I don't need to find the h. It didn't ask what the dimensions were. It just said find the least amount of material. Okay, so I'm going to take this number and plug it in here and plug it in here. Actually, I'm going to use this number. So I'm going to take that number. Oh, it's still there. I'm going to take that number, second answer, and I'm going to store that number in x. Okay, so I have that number now. That's my radius. And so I want 2 pi times x squared plus 3200 divided by x. And I get my minimum surface area, 757.288, and these would be centimeters squared. Okay, so there we go. Wow. I mean, let's think about the calculus. Once I have SA, I just have to take the derivative. Ooh, I have to bring down the 2. Ooh, I have to remember that's r to the negative 1. The calculus is not hard. Taking the derivatives is not hard. The determining maxes and mins. No, that should be manageable. Writing all the justifications. We have not yet claimed that surface area is the least when radius is this. You need to write that justification. Anytime we do max or min, you have to write that justification. Okay? I think the hardest part of these problems is not the calculus. I think the hardest part of these problems is being the master of your pre-calc. Okay. Calculus dog. Oh, I love calculus dog. Okay, calculus dog. So it turns out, I actually have the article still. Here you go. Dog runs math calculations. Okay. Tim Pennings, a math professor at Hope College, was playing on the beach with his Welsh corgi Elvis when he noticed something remarkable. Elvis was doing math. The dog wasn't ciphering with a calculator. Rather, he was acting out the solution to a calculus problem. No kidding. No, we know that. How exactly did Elvis show a knowledge of calculus? Pennings was playing fetch with Elvis that day and throwing a ball at an angle far into the surf. To retrieve the ball, Elvis might have taken the shortest route. Okay, so, there it is. And he could have swum right to it. But he didn't do that. And this is where Tim is throwing. He's throwing it up there. And so Elvis could have jumped in the water right here and swum all this distance. But Elvis didn't. He might have taken, but the dog can run much faster than it can swim. So to get the ball in the shortest amount of time, see that there? Shortest time. What are we minimizing? Time. We want to write a time equation. Can't wait. Elvis ran along the beach for a certain distance before lunging into the water and swimming the rest of the way. So Elvis ran down the beach and then swam this. Now remember, this length is still bigger than that length. So this is more running and a shorter swim. This is a short run and a short swim, and this is a very long swim. So let's figure out what happened here. So to get the ball in the shortest time, Elvis ran along the beach for a certain distance before plunging into the water and swimming the rest of the way to the ball. Using a formula in calculus that you are about to use, the mathematician could determine the exact spot on the beach where Elvis should have jumped into the water to minimize his retrieval time, to find that point. Okay? Several days later, Pennings tested his observation by taking Elvis back to the beach and clocking the dog's running and swimming times. Then Pennings tossed the ball into the water 35 times over 3 hours, and each time measured the distance to the ball and the distance Elvis covered on the beach before jumping into the water. We stopped only when the waves got too high. Elvis had no interest in quitting. Back in his office, Pennings plugged the measurements into his formula that revealed where on the beach Elvis should have jumped into the water to minimize his time. The spot changed position with every throw because the angle and distance of the ball was different each time. But Elvis came within a foot of that spot on most occasions. So can I just say, whoa, calculus dog. Now, about this time equation. So here we are. We've got dog. We've got dog runs down beach and dives into the water. I'm going to call this X. Oh, by the way, we're going to make this be 8 kilometers. We're going to make that poor dog suffer. We throw this down, and the ball lands heroically 3 kilometers out to sea. If this whole distance is 8, and this distance is X, how long is this? 8 minus X. Okay, so this is the point that we're thinking about, where Elvis runs down the beach and then jumps into the water and swims. Elvis could swim the whole way. Elvis could run further and then dive in for the shortest swim. But what we're about to find, and what Dr. Pennings found, was this is the sweet spot that minimizes, what was it? Minimizes time. So I have to write a time equation, okay? So how do I write a time equation? Well, actually, you learned it in middle school. Do you remember this one? Distance equals rate times time. This is my time equation. So if I divide both sides by rate, I get time. Time equals distance divided by rate. So it's the distance down the beach divided by the rate at which the dog runs. I've got the dog running at 8 kilometers per hour, and I have the dog swimming at 6 kilometers per hour. But this distance divided by rate only gives me the time for the land portion of Elvis's run. Elvis still needs to do some swimming. I know that this is X and this is 3, so I know that this hypotenuse is the square root of X squared plus 9. This is the distance that Elvis is going to swim. This is the distance that Elvis is going to run. I need to take the run time plus the swim time. And swim time is going to be swim distance over the rate for swimming. And the rate for swimming is 6. So there's my time equation. Here's my time equation as a function of X. Well, guess what I get to do? I get to take the derivative of this. I get to take the derivative of this and set that derivative equal to 0 to find out what X in order to minimize time. Now, before I do that, I kind of want to do a little algebra. See how this is the square root of X squared plus 9 over 6? Yeah, I don't want that. I want this. In fact, I don't want the square root. I want to the 1/2 power. Okay? And then here, I want to split this up into 2 fractions. 1 minus 1/8 X. Because I think that's going to make for an easier derivative. Using your algebra simplifying skills will make for an easier derivative. So t prime, well, the derivative of this is 0. The derivative of this is negative 1/8. The derivative of this, I'm going to bring down the 1/2. 1/2 times 1/6 is 1/12. I'm going to leave the inside alone. I'm going to subtract 1, but then I'm going to come back and multiply by the derivative of the inside. Okay, so I got a t prime. T prime equals negative 1/8 plus 1/12 on 1 over square root x squared plus 9, and there's a 2x on top. And yeah, I could cancel. I think that's a good idea. And this is what we want to set equal to 0. Okay, so let's set this equal to 0. And I'll add 1/8 to both sides. So I get 1/8 equals x over 6 square root x squared plus 9. Okay, so let's do some cross multiplying. 6 square root x squared plus 9 equals 8x. And now you need to square both sides. You may actually want to bring this over here. And so that's going to be 4/3 x. So when I square both sides, on the left side, I've got x squared plus 9. And on the right side, I have 16/9 x squared. Well, if I subtract x squared from both sides, I'm going to get 9 equals 16/9 minus 9/9 is going to be 7/9 x squared. Multiply both sides by 9 over 7. And I get x squared equals 81 over 7, which means x equals 9 over root 7. Okay, so time seems to be t prime minimized when x is 9 over root 7. Now, I wish I had my t prime. Oh, I do have my t prime. So here's my t prime. 9 squared is 81. Square root of 7 squared is 7. So I have 81 over 7 plus 9 under the radical. Well, you know what? That's always going to be positive. So I got a positive here. Nice. And then let's find some values. What is this about? This is between square root of 4 and square root of 9, which is between 2 and 3. 9 divided by 3 is 3. 9 divided by 2 is 4.5. So I want a number between, I want to be on the other sides of 2 and 3. So I'm going to plug in 1, and I'm going to plug in, is it a 5? 4. 4 would be better. Oh, but that could be 4. 9 divided by square root of 7. And that's 3.4. Oh, I can use 4. And the reason I wanted to use 4 is because 4 squared is 16 plus 9 is 25, and the square root of 25 is 5. So that's a convenient square root. Okay, so what happens? I plug in 4. I've got 4 positive over, I'm not going to know unless I actually chug through this. So 4, that was 5 on the bottom, 4 on the top, so I've got 4/5 times 1/6, and then minus 1/8. So that's going to cancel, and this is going to be 15 on the bottom, so 2 over 15. Well, 2 over 15 and 1 over 8, because that's almost 2 over 16, because I got to make a common denominator. So let's see. This is going to be negative 15 plus 16 over 8 times 15. And I end up with a positive number there. So t prime, and the value was 9 over root 7. I plugged in a 4, I got a positive. Well, that's great, because I'm looking for this to be a minimum. And if I plug in something over here, plug in 0. 0 over 3 times 6, 18. 0 over 18 is 0, plus negative 1/8. I get a negative. Nice. So time is minimized when Elvis is at this x value. Wow. Okay. I feel like I have a different answer here. Oh my goodness, somewhere there's an algebra mistake. I had this. This is my t prime. There's the minus 1/8. The 2 and the 12 cancel. There's the x, and there's the square root of x squared plus 1. That's all right. So somehow here, I got that x is supposed to be 3 root 3 over root 2. And that's not bad. Oh, this is interesting. Well, let's go find that mistake. Okay, I've got 1/8. I think it's time for this marker to be done. I've got 1/8 equals, because I'm moving this to the other side because that was equal to 0, x over 6 square root x squared plus 9. Okay, so then we had 6 square root x squared plus 9 over 8 equals x. And I multiply both sides by 8. And then I squared both sides. Okay, square both sides. So 36 times x squared plus 9 equals 64x squared. So 36x squared plus 324 equals 64x squared. I'm going to subtract 36x squared from both sides. 64 minus 36. I've got to do some borrowing. That's going to be 28. Okay, so I've got 324 equals 28x squared. Divide both sides by 28. 324 divided by 28 is, ugh, really? Did I make another mistake? No, I didn't. I end up here with 27 over 2. And so I take the square root of both sides, and that's going to be, these boards just aren't big enough. That's going to be 3 root 3 over root 2 equals x. Huh, that's not bad. Oh, I'm sorry about that. But conveniently, we had the sign change. So this, if I rationalize, is going to be 3 root 6 over 2. Okay, and when I put 3 root 6 over 2 on my t prime sign chart, I do in fact get the same signs. All right, so this is how far he has to run down the beach. We need to write our justification for this minimum. And that's all we were going to find. Our picture is, I guess you could say if this distance is 8 and this distance is x, he really has to run 8 minus x because you're here and Elvis has to run to here. So I really want to say 8 minus 3 root 6 over 2, which I guess you could do a common denominator with, 16 minus 3 root 6 over 2. So Elvis has to run this many kilometers down the beach in order to minimize time to retrieve, and don't forget to write the justification for that time. Remember, you need to say that time is minimized when Elvis runs this far down the beach because to the left of x equals, what was our x? Here. To the left of x equals 3 root 6 over 2, t prime is less than 0, and to the right of x equals 3 root 6 over 2, t prime is greater than 0. Woof. Okay, now, this is the 11th problem. And I think what I'm going to do is stop here and tell you that, I could actually have 4 or 5 more problems to do if you wanted to do some more problems. But for right now, I think we're going to stop here when we're done with number 11. And I'll make another video if you want some more problems, okay? This problem, number 11, actually was an AP free response question. And wow, everyone was so mad at this problem. And I'll explain why at the end. You have 20 inches of wire, okay? You got a big piece of wire. And you're going to cut that wire somewhere. And what you want to know is, where do you cut the wire in order to take this piece and turn it into a square with the largest area, and this piece you're going to turn into a circle with the largest area. Okay? And I want to know what's the maximum combined area possible. And at what x should we cut the wire to produce this maximum combined area? Okay? So, yeah, hold on tight. And no, really, they did do this. It was a while ago, but this has been done to students. So I want to take this piece of wire and turn it into a square. That means I have to turn this into this, 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 and this. So this is perimeter. I have this is the perimeter of the square. Okay. And this then is going to be fashioned into a circle. So when I take this wire and roll it up, I'm going to get this wire turning into this circle. So that's the circumference of our circle, just like this piece is the perimeter of that square. So here's what I want to say. I want to say this whole thing is 20, and this is x, and this is 20 minus x. You know, some sort of arbitrary cut. I'm going to turn this into a square, which means I have to take this perimeter and turn it into 4 equal sides. I know perimeter is 4x for a square. Our perimeter is, 20 minus x. Oh, let's go with side length there. That was my problem. Is 4 of those side lengths. Okay, so, and here, the circle, I'm turning this amount into x equals 2 pi r. So I'm going to divide both sides by 2 pi here and get r equals x over 2 pi. And here, where we have 20 minus x equals 4s, I want to solve this one for s. So 4, 4. And I end up with 5 minus 1/4 x equals s. Now, why did I want to do that? Because I'm trying to maximize area. The area for this shape is side squared. So side is 5 minus 1/4 x. Area equals 5 minus 1/4 minus 1/4 x squared. And over here, the area for this shape is pi r squared. And the radius is x over 2 pi. So a equals pi x over 2 pi squared. Or pi x squared over 4 pi squared. That can cancel with that. So I've got an area formula. I got an area formula. And I want the combined area to be as big as possible. So the combined area is going to be x squared over 4 pi plus 5 minus 1/4 x squared. There we go. There's my area as a function of x, where I cut. All right, you may well find it much easier if you pull out that 1 over 4 pi and just take the derivative of x squared times that constant. And here, you might find it easier also not to use the chain rule, but to FOIL. I think I'm actually going to use the chain rule here. I was thinking I was going to do, I was going to FOIL it out first, but I think I've changed my mind on that. Every time I erase this stuff, I feel like I'm going to need that again, and I probably will. Okay, so a prime. A prime is going to be 2x over 4 pi. I bring down the 2 to 5 minus 1/4 x to the 1 times the derivative in here, which is negative 1/4. I can do a little tidying, this and that, this and this. Okay. So a prime is going to be x over 2 pi plus minus 1/2 times 5 is minus 5 halves, and minus 1/2 times minus 1/4 is plus 1/8 x. All right, we want a prime equal to 0, so I'm going to move that 5 halves over, and I get x over 2 pi plus 1/8 x. Yeah, I kind of want to multiply everywhere by 16 pi, so I'm going to have 80, 16 pi, 16 pi, 16 pi. So this will cancel out. 8 pi times 5, 40 pi, equals 8x, and 2 pi x. Okay, that's good. And then I'm going to factor out an x and have 8 plus 2 pi equals 40 pi. And if I divide both sides by 8 plus 2 pi, I get my x value. Ooh, what's that equal to? Okay, so 40 pi divided by, parentheses, 8 plus 2 pi. And I end up with x equals 8.798. Phew, which is exactly what I got the last time I did the problem. It's always nice when, it all works out because there's so much not calculus here. So we have this x value, and we also have 0 and 12. Okay? So let's make a little a prime sign chart. Here's a prime. Okay, make a little a prime sign chart. A prime, 0, 20, 8.798. All right, so let's plug something in, like 0. These go away. I got a negative. Okay, and now what's something bigger than 8? 10. Is that going to help me? Not here. So if I plug a 10 in here and a 10 in here, I'm going to have 10 over 2 pi, which is 5 over pi, minus 5 halves, plus 10, I should not use 8. 10 over 8 is 5 fourths. Okay, so 5 divided by pi, plus 5 divided by 4, minus 5 divided by 2. And I get 0.3415, and that's positive. So that's a minimum. Wait a minute. That's a minimum. Didn't the problem say we want the largest combined area? Yeah, it did. But when I found that critical number and I put it on my a prime sign chart and tested, that's the minimum area. The minimum area occurs when x equals this. Well, where the hell's my maximum area? Is exactly what those kids were saying. And what those kids were saying was, no, the maximums were at the ends. From this point, A is decreasing. That's a max. Up to this point, A is increasing. That's a max. The maxes were at the endpoints. Yeah, I know. So, remember that this was x, and x was the amount of wire used to make the circle. Okay. Oh, I guess I really need these. I really need the area formula again. What was the area formula? Oh, I have it right here. Area we have x squared over 4 pi was the area of the circle, and the area of the square was 5 minus 1/4 x. No, that's the side length. I want to square that to get the area. Okay, there's my area function. Now, if x is the amount of wire used to make the circle, and I plug in x equal to 0, that means I'm using none of the wire to make the circle. And so that becomes 0, and I put a 0 in here, and I get 5 squared, or 25. So a of 0 equals 25. This is no circle, only square. But what if I use all of the wire for x, I use all of the wire for the circle, and none of the wire for the square. Okay, that's a of 20. And so when I plug a 20 in here, 20 divided by 4 is 5. 5 minus 5 is 0. Area of the square is gone. I just have this. 20 squared is 400 over 4 pi, or 100 over pi. That's 3.14. 100 divided by 3-ish. I think that's 30-something-ish, which is bigger than 25. The maximum area comes when we put all the wire into making a circle and none of it into making a square. And the kids were so livid at College Board this year because the problem was written in such a way as to suggest that you needed to have some of each of those. Yeah, no, it turns out the maximum area occurs when you make only circle, no square. Okay, and if I want to know what that maximum combined area is, I can just, oh, that is my maximum combined area. Never mind, done. Okay. Wow, that was a lot of problems. Is your brain still there? Okay, shadow problems. I noticed that we didn't do any shadow problems, and I have a suspicion. Oh well, that's no shadow is related to this. I think we've got all this. Ooh, the trough problem. You know, if you're looking for a challenge, do the trough problem. Another volume of the can, volume of the can. Yep, no, we've covered all the different types of problems. And notice how many of them were types of problems that you actually saw in pre-calc. I mean, we really did spend a lot of time doing that. All right, so this, even though it comes in at 1 hour and 48 minutes, is really 3 videos, okay? It's, I think it's 66, 67, 68. It's all of our videos for optimization, unless you decide you want another one. If you want another one, I'll make you some more. I've got some more problems here. But we've done all the different types of problems, okay? So you've seen them all. And now I would say you should really practice them. Because, yeah, you need to practice these. Okay, so have a wonderful day. And remember, it's this video for 3 lessons. Oh, assignment 67, 68, and 69. Sorry. Okay,